Um, I just want to see if you can hear me. Can somebody reply in a chat? Super, super. Okay, then welcome. This is the Bayesian machine learning class, and today's lesson is about Bayesian machine learning. So what I'd like to do is first some announcements, then we go into basically the Q&A for this class. And then in the end, Wouter wants to say a few words on how to prepare for the next class, which is going to be a programming class. First, the announcement. We did a poll on whether we should continue with MS Teams or with this framework for this Canvas, but I think it's made by Big Blue Button or something. And the poll came out that people want to try MS Teams. So my proposal is that we're going to start next Wednesday with MS Teams and see how that's going. Not this Friday yet, because I first have to find out how I'm going to set that up with a class of 120 people. So you can expect probably a message in the next week with an invitation for an MS Teams class. I don't have any other announcements. So from my viewpoint, we can start with so Q&A on the Bayesian machine learning class. One thing I'll say about this lesson is that this lesson and also the previous lessons, so the probability theory and this Bayesian machine learning lesson, are conceptually the most difficult lessons in the whole class. There will be one lesson towards the end, I think it's called latent variables and variational Bayes, if I'm not mistaken. There's also a computation or a conceptual step, but aside from that, it's pretty much a matter now of making model proposals and working out the equations that we've developed in this class. And this class, this Bayesian machine learning class, if you understood it well, then you might have found that it's really just an application of the sum and product rules, right? But underlies here is Bayes' rule, whether you're talking about parameter estimation or model comparison, which you can also call it model estimation. It's the same rule. It's Bayes' rule, and Bayes' rule in principle is just the product rule, although in order to let's say to compute the evidence which you need to compute, you need to do marginalization, which is the sum rule. So you get to play with all operations, sum and product rules in if you want to execute Bayes' rule correctly. But basically, that's the whole idea of this lesson, to show that in principle Bayesian machine learning is a conceptually simple application of probability theory. So with that, I'm open for your questions. You can either turn on your microphone or write something in the chat, and then we'll talk about it. It can also be, of course, about something on Piazza. It can be about anything, but let's stick to Bayesian machine learning. Okay. I don't see any questions. Is that correct, that I don't see any questions? Which is totally fine with me. That means that, okay, I think a question is coming. But from my viewpoint, this, the real, so it's, and I said that before, these sessions can be very short. I mean, I hope they're short. I hope everything is clear in the lecture notes, the video guide, and that through the discussion in Piazza, basically the remaining questions are resolved. And this is just a double check, if you will. And we can keep this very short. It's, as you know, we're also going to post it on the website. And I'd like to keep the videos as short as possible, right? You don't want to listen to 2 hours of video with just 5 minutes of information. So I'll give you another 30 seconds to come up with a question about anything. Are there anything in Piazza, perhaps?
I did have a short question.
Yeah.
About something in the reader, like at the end of the reader for this lesson, it says the maximum likelihood is an estimation is an approximation to Bayesian learning.
Yes.
But I don't think I really grasp that as a concept, because you have the maximum likelihood estimator where you have no prior knowledge, and how do you predict a Bayesian machine learning is basically based on the fact that you have prior knowledge. So
okay, yes. Well, that's a really good question. So let's go down. I'm not sure. Do you? So just asking. Do you see do you see my screen that I'm showing here, the Bayesian machine learning class, and
yes,
I'm scrolling?
I see it.
Oh, okay, super. So I'm scrolling down because I don't see it myself. Okay, I'm scrolling down. Yeah. So basically, so Bayesian machine learning computes this, right? The posterior for the parameters. And so what maximum likelihood does, and some other point estimators, in a sense, you can say it approximates this posterior for the parameters by a delta distribution on one value. In that sense, it's an approximation. Let's say this is full Bayesian machine learning, right? And this could be a Gaussian, or it could be some wild distribution. And now it's a function over theta. And now I'm going to say, okay, now this integral may be hard to compute. I want to compute here the prediction for x given all the past observations, but this is an integral I cannot compute, right? So I'm going to do something simpler. This posterior here, I'm going to approximate that just with delta function, like here, right? So if I do that, then I can execute this integral, right? Because yeah, this integral is really just this function, this data generating function evaluated at theta hat. So I just evaluate my data generating model that I've proposed myself at theta hat. And so maximum likelihood is this estimation is a particular choice for theta hats. There are other choices, right? I can have I can have any kind of function, and I can take the mean, the mode, I can do whatever. One way to choose delta hat is just take the mean. This is the mean of the posterior. Another way is to take the maximum of the posterior. And right, that's what we do here. It's called the map estimate, the maximum posterior estimate. And if it's a Gaussian distribution, this posterior, they would be the same. But if you have a, I don't know how to draw. Maybe I can draw. Let's see. No, that's not going to work. No, I don't know how to draw on this. But if you can imagine, I have some kind of a strange function, let's say something like this, and I could, I could pick I could pick the max the maximum likelihood estimate is also a particular choice, namely. From our full model, having a prior and and let's say a likelihood function, we only take the maximum of the likelihood function. We don't care about the prior, which basically says this prior equals, it's constant, right? It's 1, or let's say a constant over the domain of. So in that sense, it's a particular choice for theta hat, and then plugging that in as a posterior. In that sense, it's an approximation. It's an approximation of this function here by this function. Is that clear?
Yes, well, yeah, but that means that, for example, in the coding example which was given, where you saw that if you use the beta distribution, that if you have enough sample points at some point, there's going to be no difference between if you would have a prior or not.
Okay,
so the prior becomes less important the more samples you have. So is then the maximum likelihood estimate. If you have enough data points, would the maximum likelihood estimate become almost equal to the Bayesian method?
Yeah, in the sense that, okay, so I mean, this multiplication here, the prior times the likelihood, is going to be proportional to the posterior, right? I just need to divide by P over D. And so there are two components here. There is knowledge that I just throw in there by prior knowledge, and there is knowledge, yeah, coming from your likelihood, which basically summarizes all knowledge from my data. Now, if I get a lot of data, this is usually a very sharply peaked function. The more data I get, the more sharply peaked this gets. Because one reason is that you can imagine that, let's say, if for individual data points, this is a Gaussian, and then P for D is going to be the product of all these Gaussians, and it's going to be a really sharply peaked Gaussian with a very small variance. So then this product of P theta times this function is going to be dominated by this likelihood function. So and you see that also here, right? In the beginning, so we have no data points, or maybe a few. I think n is 3 here. Okay, so there's quite a difference between these two scenarios where we have different priors, and the data is the same. But so for one prior, this is our belief, and for the other prior, this is our belief. Now, if I get 150 data points, they're almost the same. Now, so you can say, and this function here is almost the same as the likelihood function, because this function is going to be, it has a very high value and a very narrow base. So if I multiply it with whatever the prior is, well, there's not going to be much difference. Now the maximum of this function is here. That would be the maximum likely estimate, right? So around 0.4, maybe a little less at this moment. And if I would go through even more, then hopefully the real mu was 0.4. I'm going closer and closer to 0.4. So yeah, maximum likelihood estimation will get closer and closer to, let's say, to the real underlying value. But what you don't get from maximum likelihood estimate, you never get this uncertainty. So in a sense, you never know how much uncertainty there is. If I see this posterior here, I can say, okay, my mean is 0.39. But I also can say, and I have high confidence because, yeah, I see this curve. But if I just do maximum likelihood, I can say, yeah, my maximum likelihood estimate is 0.39. And then you can ask me, so how confident are you about that? Is 0.388 completely wrong, or is it just mildly wrong? And you'll have to say, I don't know. I just got 3.9. That's my maximum likelihood estimate. But if I have this curve, I can say, well, 3.9 is also good, but 0.5 is wrong, right? You see that from this curve. So this curve gives more information. The Bayesian estimate, the posterior, gives always more information than maximum likelihood estimation. Because maximum likelihood estimation is just an approximation of this curve, with a delta. And so it says nothing about the value that is right next to the delta. And this curve at least tells you something about the whole domain. So it never gets equal. I would say if you get more data, then maximum likelihood estimate, it becomes, let's say, a better alternative than, or becomes a better, yeah, it's becoming closer and closer, let's say, to proper machine learning, because yeah, the information in the data is going to outgrow the information in the prior. But you'll never be able, there is still a few disadvantages to maximum likelihood. You'll never be able to say something about the value here, theta hat plus 0.1. Yeah, I don't know, right? You would need to have to go to this whole function, to the likelihood function, and not to the maximum likelihood estimate in order to say something there. The other thing, what is good about maximum likelihood is, and why people use it, well, it makes all the equations easier, right? If I want to predict something, I don't have to integrate. So it is a computationally very advantageous alternative. And if you have a lot of data, then it's also usually quite accurate. But it's very hard to say how accurate. That's the problem. Because you cannot do with maximum likelihood estimation, you cannot compute the Bayesian evidence. It just blows up or it goes to zero. So that's a bit of a problem with maximum likelihood estimation. You get an answer, and if you have a lot of data, it's probably a good answer, but it's very hard to say if it really is a good answer. But then again, it's easier to compute. So there are trade-offs. Is that a bit clear?
Yeah, that was way more clear.
Yeah, sorry, I went on too long for it about it. I have a tendency to keep repeating myself, and you can just stop me when it's okay.
If I may add to that, Hanna, you said in the case of a lot of data, you in really complex. This is a one-dimensional example that Bert showed. In really complex problems, you need a lot more data than Bert just showed. You need millions and millions of samples to get that asymptotic behavior out. And so when you run a maximum likelihood estimator on a real-world problem, you often don't know whether you have enough samples to do that.
Right. So I see a few questions in the chat, and I think we should just go through them from the top. So one is, I did not fully get the fourth question from the Bayesian machine learning part. So let me see if I can show that question. Do you see the questions now? So what is exactly the problem here? The fourth question from Bayesian machine learning. This one. 4A. Oh boy. I haven't looked at this one for a while, so let's see if I can do that. We make a number of observations, have the following model: xk is a plus epsilon k with known variance. We're interested in deriving an estimator and derive a Bayesian estimate. So there's a prior here, a Gaussian prior, and there's going to be a Gaussian likelihood. So P of A here is this Gaussian. This here is the likelihood. And yeah, okay, so the problem, okay, I see we are a bit ahead of ourselves here. If we multiply a Gaussian by a Gaussian, you're going to get a new Gaussian, but this is something, okay, that we actually will discover in in 2 lessons. So this may be the problem. And to go, let's say, from here to here, you need a rule that you can find. Let me see. In the notes by, unfortunately, if I click here, it downloads it. In the notes by Semron Wise, if you go to Gaussian identities, I could also show it, by the way, here, the Gaussian distribution, B5. So you're totally right. It's a bit out of order. But what we will discover in this class is if we, let's say here, Bayesian inference for the Gaussian. It's exactly this problem, right? If I have a Gaussian likelihood, I have a Gaussian prior, and then we multiply Gaussian times a Gaussian, and we can work that out to this. And in more general terms, a Gaussian times another Gaussian gives another Gaussian. But you are right, it's a bit out of order. I should have put a note there in that question. Is that okay? Good enough for an answer? Then based on question 25 in Piazza. Let's go to Piazza. I don't know how to get to 25. Is it this one? That's 30.
It's the question regarding model comparison. A bit lower than that.
Ah, this one.
Yeah.
Okay, super. And the question is why we don't need a test set. I would turn it around and say, so aside from normalization, right? I mean, what do you really want? How in Bayesian machine learning, you want to state or you want to update your state of knowledge about something when new information comes available. So in this case, new data becomes available, right? So if you want to state your knowledge about parameters, well, what do you want to know? The most natural way to express that is, I want to know the probability, my state of knowledge about parameters, given the new data. And then Bayes' rule tells you how to do that. And it's really the same thing for model comparison, right? The probability for MK given the new data, and this is how to compute it. There never is something like a test set needed. It turns out, and I hope to have done that. Have I done this here or here? Okay. So if you would read on a little bit in Bishop, you'll see that the evidence, the Bayesian evidence, consists of accuracy. This is basically how well we can predict something, and model simplicity, or model. Sometimes it's also with a minus sign, model model complexity. Now, what we want to do is we want to choose models that have maximum evidence. That means we want to have maximum accuracy and maximum simplicity. This maximum simplicity is sort of what you do if you have a test set, right? If you would not have a test set, the problem is that if you just do machine learning and not in a probabilistic framework, then you don't have a prior. So this term does not exist. And that means you only care about accuracy. Accuracy means how well can my model, my neural net or my model predict the data. Well, there is I could just keep growing the size of the network, keep growing the size until my neural network or my model becomes sort of a table lookup. And then, yeah, I can predict the data perfectly. So that would be the best model. But that's not the essence of a model. A model is let's say, is a summary of data, right? You don't want to have a model that has a larger let's say, memory footprint than the data, because you might as well store the data. A model is, you want to capture the patterns in the data. So you want to have simple models. Now that is built in the Bayesian framework. The Bayesian framework leads naturally to simpler models. You don't have to do anything for it. You cannot overtrain. But if you throw away your prior, then you can overtrain. That's that's what happens in maximum likelihood. There's no more prior, and then you can overtrain. And in order to avoid that, yeah, then you need a test set. You just want to say, okay, here's a holdout set of data. I'm just going to see how well my model predicts a data set that I do not train on. That's a totally fair, let's say, ad hoc mechanism to kind of check the performance of your model. But it's not as principled as just computing the posterior for the model. Right? The only thing is that if you do a posterior for a model, yeah, then you need a proper prior. But if you don't do that, if you don't have, I mean, if you go to, let's say, the traditional machine learning, the not probabilistic, there's also all kinds of assumptions, right? You need to set your initial values of your weights, and depending on your initial values, you wind up in a different place after you've trained. So that's why you say, okay, no, but I'm going to train 100 times. I'm taking the average, and so you keep adding let's say ad hoc mechanism upon ad hoc mechanism to kind of make up for the fact that you don't have a prior. I would say Bayesian machine learning is really, let's say, the proper framework. If you cannot do that because it may be computationally impossible, okay, then we need to do something else. We may say we don't have a prior for models or for parameters. Okay, well, then we have a problem in how to stop training. So then we start adding mechanisms like, oh, but how about if I add a test set? And yeah, then I'm still sensitive to initial conditions. Oh, well, how about if I just do it 100 times? And so I keep adding to my mechanism to come up with something, but it's just not as principled as just updating your state of knowledge. I used to know this PM of K, and now I know this PM of K given D. It's extremely simple and correct. So my the question, why do we not do test set? I would turn it around, is why do we use a test set? Well, you use a test set because you've decided to not do Bayesian machine learning, and there may be very good reasons for that. But it's because you cannot compute this that you need to come up with mechanisms to stop training. Bayesian machine learning, you cannot overtrain. Does that make sense, or am I just rambling here? Okay, during the video lectures, I briefly mentioned the normalization constant, but dropped it during the computation. Why should it be used for? And when is it okay to disregard? Okay, so if we go to the posterior, let's say here. So here's a posterior, right? I mean, this is for model, but it's the same for parameter estimation. So this is Bayes' rule. And here in the second step, I think you can still see, by the way, my screen, right? Because I don't see it. For the beta distribution, it's the same as for this. It's for any distribution, the same thing. The idea is that this is if I'm interested really in just the probability distribution over MK given the data, then I know that summed over all MKs, this is going to add up to 1. I know that because it's a probability. So as a function of MK, I can sum this to 1. P of D is not a function of MK. So with respect to MK, this is just a constant, it's a value. Yeah, we need this value because let's say P of D, because this will actually make sure that P of MK actually sums to 1. Because if I make on both sides the sum over P of MK, note what happened to the denominator here, nothing, right? But to the numerator, this is really the joint PD comma MK, and if I sum over MK, I get PD. So what will happen is PD divided by PD. So by dividing the numerator here by PD, I have made sure that this is indeed on the left-hand side a probability that adds up to 1. But if we now actually do that in practice, and we do it, for instance, for this beta distribution, all right, you see that this normalization thing, right? I mean, this is a function, beta is a function of mu, right? And the mu terms is this guy, and here 1 minus mu, beta minus 1. And this here, all this gamma stuff, that's my normalization. Now, when I multiply these guys, yeah, I'm going to have to multiply gammas over alpha plus beta and alpha minus 1 and beta minus 1. I get a whole bunch of gammas here. But I know that if I do that, then in the end, all I'll get is just a normalization factor for this guy. And this guy is a beta distribution. And I know it's going to be a beta distribution. Because I mean, Bayes' rule will make sure that the left-hand side is a beta, is going to be normalized. And the only distribution that fits this template of mu to the power something 1 minus mu to the power this, that's the beta distribution. So I'm not going to have to actually calculate that normalizer, because and Bayes' rule will take care of the fact that this is going to be normalized. I only really care about, let's say, I only really care about the numerator. The normalizer, this evidence will make sure that this is going to be normalized. But I often don't have to compute it. Okay. How the Bayesian, okay, so I'm going to continue to the next question unless somebody stops me. How does Bayesian machine learning deal with outliers in the data? If we use all the data to train or model or update our belief, or do we sometimes pre-process the data to exclude these outliers? Yeah, that's a really good question. So there, you have to. I mean, as an engineer, you have to make a judgment call. Is the outlier a result of something that went wrong, right? Something that you measured wrong. So then it wouldn't be fair to try to include it in your likelihood model. Right, because yeah, something went wrong here. My sensor got decoupled from my, or my sensor broke down. So yeah, I get outliers. Then that's an outlier. By an outlier, I mean that there's a very low probability under the data generating distribution. right? That's what I mean by an outlier. You have to make, when you do Bayesian machine learning, you have to come up here with this guy. This is a data this guy here, a data generating distribution. And an outlier, I mean that no matter what you choose for theta, the observation that you make is going to be very unlikely. That's what I call an outlier. And if you think that that's due to there's a measurement error. I mean, you didn't pay attention, or whatever. You wrote down a 3 and somebody else read a 9 or something. Something went wrong. Then you should take it out. However, if you think, yeah, this is really what happened. I mean, it looks really bad. I mean, it has a low probability, but this is what happened. Then I think you should just include it, and you should, and probably you'll find out if you do model comparison that you're not going to have a very high evidence for this model. So you should continue your search and maybe come up with a better data generating distribution that would give a higher weight to the outlier. In the end, there's only two things here. You either include it, you either decide this is really proper, this is what happened, and then you want to model it, or you decide I want to throw it out. So, but I think you can only do that if you decide that something went wrong in the measurement process. If the measurement process was actually right, you say, yeah, this is proper data, then probably you should be looking for a better data generating distribution. Okay, so then the next one. When for a specific model, we have to calculate the integral of a function that we do not know the integral of. I guess we resort to numerical methods to evaluate the integral. Yes. How accurately does this approximation need to be for a good estimation? And is there any application where we actually do this? Yeah, so as you've seen, in Bayesian computations, you need to do lots of integrals, right? For prediction, you need to integrate out over the parameters, and also for the evidence, you need to integrate out over the parameters. And that can be difficult. Sometimes it may be, let's say, analytically intractable, and then we need a numerical method. Yeah, there are numerical methods, Monte Carlo simulation. Yeah, that's where the research is, right? One of the problems of numerical methods, such as Monte Carlo simulation, is that often we get an answer and we don't really know how good the answer is, because Monte Carlo simulation by itself is often not Bayesian in the sense that it doesn't give you an answer plus uncertainty about that, right? Plus some error bounds. It just gives you an answer and say, oh, this integral comes out to be 10. What you'd really want is some distribution around 10. So yeah, so some uncertainty, and many Monte Carlo, let's say, numerical methods for integrals do not do that. So if you want to actually know how accurate your approximation is, you should choose an integral approximation method that actually, let's say, that's Bayesian in nature, that gives you a posterior over, let's say, over the outcome of the integral. There is, yeah, I think there is some work going on in this. They call it probabilistic numerics. Let me see if I can find it. Probabilistic numerics. So here, this deals with what you are talking about, right? When you do numerical computation, you want really as an answer, not just, let's say 5, but you want to say 5 plus or minus 0.1. And that's what this is about. And so it's an effort to make numerical computations more Bayesian. Okay, good. We're about 40 minutes in the class. I mean, I don't mind to keep talking, but I don't see a question at the moment. Are we about done? I mean, I'm also totally happy to continue any conversation in Piazza. I mean, it's not like because we put the Bayesian machine learning lesson now behind us that you can't post any question in there. I mean, you can post a question in basically in any folder there in any lesson. So don't worry about that. We can always revisit this. Okay, I may be mistaken, but I think I've answered the question. So if you have no objection, I'm just going to ask Wouter then to to tell you a little bit about how to prepare for Friday. And so then I'm going to stop now the review of the Bayesian machine learning lesson. And yeah, I'm going to give it over to you, Wouter.
Yep. Yes, thanks. Yes, so on Friday we are starting with the probabilistic programming sessions. If you go to the website bmlip.nl, maybe I can open this in Canvas. Yes, so if you go to the website, there's under materials and books, there's a bullet point with my name and then the Julia and Jupyter install guide. So the point of the probabilistic programming sessions is that we go through some problem statements where we try to make some of the equations a bit less abstract. You get to play around with parameters and develop an intuition for how, for instance, shape parameters of a beta distribution actually shape that distribution. So we won't be trading new material, we'll just be going over it again in an example form, and you'll be using Julia and Jupyter to do all of the computations. For that reason, you need to have Julia and Jupyter installed. So on the materials books, there's the install guide. I would suggest having a look at this. It's arranged per operating system. And this contains all of the steps to get it up and running on your machine. And then I want you to download the source files for the course. And then under the folder Lessons Notebooks ProProg, there are 4 Jupyter notebooks with the probabilistic programming lectures. So these are W1, W2, W3, and W4. So I have also recorded a number of videos for the first probabilistic programming session. So just like with Bert's lectures, I want you to have a look at these videos, W1.1, W1.2, and 1.3. Oh yeah, that reminds me, if you're having trouble installing Julia and Jupyter, or if you just want to test your installation of Julia and Jupyter, there's a video on that under this link here. Right, so if you get everything up and running on your own machine and you've looked at all of the lectures, then on Friday we will be going through parts of the lecture notes that you would like to be explained a bit more. So I'll be running things locally. And after the lecture on Friday, I will make the first probabilistic programming assignment available. So they're not available at the moment, but they will be made available. Oh, this is the wrong course. So we have 4 probabilistic programming assignments. These are not mandatory, but they're a good way for you to check whether you've understood what happens. And they're also really fun to play around with when you want to do all of these computations in Julia and Jupyter. But I'll explain a bit more about the assignments next Friday. Oh, and now we're getting nested. Yeah. Yeah, that's it. So if you have any trouble installing Julia or Jupyter, if the video doesn't cover it and the step-by-step instructions also don't cover it, then just post your error to Piazza, and we'll help you get started.
There is a question about if people should download 1.52 or 1.53.
Oh yeah, that's a good question. So this is funny because Julia updated their version from 1.52 to 1.53 on the 9th of November, so on the starting day of the course. So I prepared an installation guide, and then a day later they updated the version. Both are fine. We just need Julia 1.5. We've tested everything against 1.5.2, but so currently if you go to the Julia Lang website, it'll just show 1.5.3. That's fine. Just download that one. That should work. So the assignments are for practice, but Bert has mentioned that so they can act as bonus points. There's a file. Yeah, PP1 assignment is the notebook for the first assignment. The notebook itself is already available, but the on Canvas there will be on the left hand side there will be a tab called Assignments, and then the Probabilistic Programming 1 assignment will be made available Friday morning, and that has the explanation of what you should do and also the format of your submission. We have a lot of students, so the notebooks will be auto-graded, and so they have to be submitted in a particular form. So I mean, you can open the notebook already and have a look. You can also do it already if you think that works, but you cannot submit it yet before it becomes available on Canvas. Yep. Are there any more questions on the probabilistic programming sessions?
Okay, so then I suggest we stop here, and yeah, we look forward to seeing you all on Friday.
Yeah, should be fun.
Okay. I'll see you Friday then.
See you Friday, everyone.